Hello everyone. Welcome to tonight's session on chirality and stereochemistry. Let's begin with a sound check. Let me know if you can hear me. And we will jump right in. If you can hear me, let me know where you're tuning in from and what brings you here today, because this is going to be an exciting session. Chirality and stereochemistry is one of those topics that it seems kind of tricky because it's a three-dimensional concept. You're learning how to find something to do with 3 dimensions and directionality of the substituent, but you're learning to do it on 2-dimensional paper. So we are going to simplify all of that today, but first I want to make sure that you can hear me. Let me know in the comments if you can. All right. You told me how to pronounce your name that last time, but I forgot. So if you can just type that in for me again, I want to make sure that I have it right, especially if you'll be participating and I have to call your name as we continue. And I know there's a scary molecule on the screen. Don't worry about it. We are going to get there very soon. Ovase. Ovase. Am I saying that right? Abdullah, it is nice to see you again. What are you working on this semester? Welcome from all the way around the world. Let me know where you are tuning in from. And it looks like we are due to kick off. So let me find my notes. All right, here we go. Let's do this. Welcome to tonight's chirality and stereochemistry workshop, where we are going to look at some amazing shortcuts to simplify this topic. Before I show you a quick and awesome shortcut for how to look at these 2 Newman projections and figure out their relationship, are they enantiomers, conformational isomers, what is going on? We first have to go back to the very basics. Oh, and I will show you this. Let me start that again. Before I show you how to look at these 2 Newman projections and easily and quickly figure out their relationship, conformational isomers, enantiomers, well, what are they? Without having to find if they're RNS, that is the beauty of this shortcut. We first have to go back to the very beginning and make sure you have that solid foundation so that you can approach problems like this quickly. Now, we are going to cover a lot today. Don't worry about copying everything down. Instead, just comment live notes for a PDF copy of everything I draw today, and I'll email it to you after we finish. If you're watching the recording, same thing, put live notes in the comments, and you will get a copy of today's session notes. Just prepare that link for you. Before we go into the big scary, let's take a step back and start with the basics, going all the way back to the periodic table, specifically the 10 atoms that come up most frequently in organic chemistry. We have hydrogen, then carbon, nitrogen, oxygen, fluorine. Going down the halogens, we have chlorine, bromine, and iodine. And then under nitrogen, we have phosphorus, and under oxygen, we have sulfur. These are the 10 atoms that will come up most often, and I highly recommend that you memorize it. You get so many things out of this. Electronegativity, up and towards the right. Size, down and towards the left, critical for reactions. But the reason we're looking at it today is when it comes to ranking substituents, when it comes to finding RNS, we're going to refer back to this table over and over, and it's much easier to know, it's much easier to figure out if you already have them memorized. And so if you haven't already, comment when you're going to work on this, when you're going to memorize it, yes, even if you're watching the recording, because this will show us how we rank our atoms when finding the stereochemistry of an atom, when finding if it's R and S, when finding if it's D or L, if you're advanced and looking at, say, Fisher projections for amino acids, everything. The way you do this is you look at the highest atomic number. The greater the atomic number, the higher the priority. And so iodine in this case is the highest priority. Then we have bromine. Then here we have chlorine, sulfur, phosphorus, fluorine, all the way to hydrogen, which is your absolute lowest ever priority. Sometimes your professors will want to make it exciting and a little tricky. They'll throw in a little D on the molecule. D is just deuterium. Deuterium is a heavy hydrogen, and it is slightly higher in priority than hydrogen itself because it's a heavier hydrogen, but it's still one of the lowest, meaning it still ranks under carbon. So we have the atoms, we know the priority, but what exactly are we looking at? Well, let's actually take a step back even further and talk about the concept of chirality. When we are looking at chirality, what we're looking at is the handedness of a molecule. Just like humans that are right and left-handed, molecules also have a handedness, and that has to do specifically with how they turn plane polarized light, or rather that's how it started. But the handedness simply tells us that when we're looking at a molecule and we have the different substituents, if I trace them in a very specific order, do they go clockwise or counterclockwise? And I think you're actually seeing it backwards. So it's simply a question of where do these things go on the molecule, no matter which chiral center you have on the molecule. So I'm throwing out a lot of different words there. Let's take a step back and actually make sure we cover all of them. In order for a molecule to be handed, to have handedness, it has to have 4 unique substituents so that you have a direction. And what I mean by that is, let's take a look again at this model. Now you'll notice this is not the typical piece that I used. My son decided to steal all the green ones. Well, he took a lot of them, but I didn't get enough green ones back. So here we are, no green ones. But if you look at these 2 molecules, they're pretty much exactly the same. I have red, white, and blue, and this bulky black one in the back. If I put them together, notice that they are, well, exactly the same thing. They're perfectly lined up. But if I did not have it this way, let's pretend for a moment that when I first showed it to you, I had these 2 molecules. All I did was switch something. Now, if I try to line them up with the black facing each other, and then, yeah, these are not, I can't line them up. Notice that I have the black ones together, the blue ones together, but the red and white are not together. If I change it so that the red and white are exactly the same, notice now that the blue and black are not the same. These 2 molecules, because they are chiral, because they follow the rules that allows them to be handed, they are opposite hands. It's a right and left hand. If I try to put them side by side, notice that they have a perfect mirror image. There is perfect symmetry between them. No matter how I rotate them, it looks like I have, well, assuming my hands are doing the same thing, it kind of looks like everything about them is perfectly mirrored. The same thing, I keep using the word handed. If I take my 2 hands, they're exactly the same. My thumbs are lined up, my fingers are lined up. They look the same, except my palms are in opposite directions. So if I separate my hands, well, if I do it like this, and yeah, I even have mirror band-aids because I tripped today during my marathon training, and let's just say I ripped my hands open very unpleasantly. So ignoring the band-aids, notice how my hands look exactly the same. They face each other. Everything I do, let's pretend that they're the same, right? Perfectly mirror images, except if I try to put one on top of the other, looks like they're perfect, except one's got the palm, one's got the back of the hand. So I switch it, have to switch the other one. The only way I could get them to superimpose is if I were to somehow take my thumb, put it on the other side. That would not we're not going to do that. But the idea here is that just like my hands are handed, I have a right and left hand. That's the idea with the molecules. And that's basically what we're trying to find out. Is it a right-handed molecule or is it a left-handed molecule? Angel, it is good to see you. I did not get a chance to respond to your email yet. I have not forgotten you, I promise. I just didn't get to respond yet. Yeah, it hurts pretty much. It's not too bad. I'm actually more frustrated that I cracked my phone screen than scraping my hands, if I'm going to be honest with you. So back to the idea of handedness. In order for a molecule to be handed, it has to have 4 unique substituents. And the reason is, if I don't have the 4 unique, Kiddo left me some white ones, so that'll be easy to demonstrate. If I only have 3 unique substituents, I have black, white, and blue, and a second white one. If I take the red one off this as well, you'll notice that if I try to superimpose them, I can. I have the white ones lined up, the other white ones, the blue and the black. But I can also make a perfect mirror image. These are perfectly mirrored because there's a line of symmetry in the molecule. Do you see how if I slice it right down the middle, I have the blue in the middle, the black in the middle, and then on either side, I have the white. Because there is symmetry in the middle, this thing can be a right hand or a left hand, and therefore it can perfectly superimpose. It can be a perfect mirror image. This does not qualify as chiral. A little bit of a circular introduction there, but hopefully we're on the same page. You're typically not tested about the why behind it. This is all just leading into, okay, so we have a molecule that is 3-dimensional. It has 4 unique substituents. And if I have the 2 molecules where one is a right hand and one is a left hand, then we get what is called enantiomers. And the idea of enantiomers is that they are the opposite pair, meaning I have the right hand and the left hand that perfectly match each other. And that is what we call the mirror images, as I demonstrated. And mirror images are considered non-superimposable. When something is superimposable, just like the molecule that had the 2 white, I can perfectly place one on top of the other. These are not chiral, not enantiomers, not mirror images. They are just superimposable molecules. Precious, it is good to see you. It's so cool how I get to, in the beginning of the semester, get to know students. So Precious, I've seen a couple of your emails already, and now I get to see you here, and hopefully all the upcoming live streams. I love seeing students come from session to session to session and just learn together throughout the entire semester. So let's see what this looks like on a molecule. I showed it to you with a model kit. Now we'll draw the molecule in 3 dimensions, and typically it'll be drawn a couple of different ways. This is how I like to draw it, where the line is in the plane of the page, meaning it is exactly lined up with the paper. The wedge is coming out of the page, and the dashes are going into the page. Let's put random substituents on there. We'll have, no, I don't want to start that way. I want to start here. Hydrogen, methyl, alcohol, and bromine. Since you may not have this memorized yet, I'm going to keep this, whoops, did not mean to do that. I'm going to keep this handy for you. What am I doing? It's been a fun day, to say the least, between falling during my run, cracking my phone. Our AC had quit, so we just, oh, that's a good point. I should turn on this. I don't know where the remote is. Our AC had quit, so we had a guy just making so much noise fixing it today. And then our oven also broke, all at the same time. It's like, I don't know, this is the week for everything to break. So I'm a little bit frazzled. If you catch me making a mistake, let me know, because sometimes I do that when I'm distracted. So we have our 4 substituents. You'll notice that this one right here is considered a chiral carbon. On a molecule, you tend to put an asterisk if you want to show this is chiral. And we already talked about how iodine is your highest priority, and you simply work down all the way back to hydrogen. So let me show you how to do that, starting with the easiest way to rank and then kind of working our way up. If you joined late, welcome. We're about to get into the meat of how to find R and S, so you are here just at the right time. Don't worry about copying everything down. For a copy of today's session notes, just put live notes in the comments and I'll send you a link. Yes, even if you're watching the recording, that way you can focus on just learning and practicing with me. So here is how you're going to rank the substituents to find if it's R and S. We'll take 4 simple steps that I promise are much easier than any craziness your professor may or may not have thought to tell you. Step number 1, you're going to rank your substituents from 1 to 4. 1 is the highest priority. In this case, I have oxygen, hydrogen, carbon, and bromine. Oxygen, hydrogen, carbon, and bromine. Remember, we start at the bottom with iodine, and so bromine is the first one. That is priority number 1. Oxygen is the second. That is priority number 2. Carbon is the third. That is priority number 3. And hydrogen is the fourth. That is priority number 4. So now I have my substituents ranked. This is the hardest piece. This was an easy one on purpose because I want to build up from easy to hard, but make sure that you're with me on what I did here. If at any point you have questions, just let me know and I'll be happy to clarify. Once we have our 4 substituents, the next thing you want to do is make sure that number 4 is in the back. I'll show you what to do if it's not, but in this case, number 4 is in the back. I did that on purpose. It is on the dashes. It is going into the page. With number 4 out of the way, we only ever rank 1, 2, and 3. So because we only rank 1, 2, and 3, we make sure to get rid of number 4. That allows the top 3 to be forward, which is forward or in the plane of the page, which is good to go. Then we are going to do as follows. Cross out number 4. And you're going to trace an arc from 1 to 2 to 3. I like to look at the top of the arc. Different people will show it in a different way. If we cross out number 4 and trace an arc from 1 to 2 to 3, notice that the top of the arc in this case is going clockwise or to the right. If the top of the arc goes clockwise, that is R. If it goes not clockwise, it is not R. That's how I think of it. So it's R or not R, and the not R happens to be S. I've also heard clockwise is the right way of the clock, the right way with an R. I don't like clockwise and counterclockwise though, because in my mind, I have to then think of a clock, think of how to rank it, and I may not necessarily know how to do that. So I just think of it as going to the right, it's R, not going to the right, it is not R, then it is S. And so for our first molecule, we have the R configuration, or the R for stereochemistry. Now you'll notice we took our time to actually rank all the substituents, but if there are shortcuts, I want to show them to you, right? That's what I promised today, R and S shortcuts. Notice on the periodic table, hydrogen is the lowest. There is nothing lower than hydrogen except electrons, which you're not going to be tested on. And so if you see a hydrogen, you don't even have to worry about ranking it. So trick number 1 is that anytime you see hydrogen, it will always, always, always be number 4. If you see deuterium instead of a hydrogen, same thing. If you see a deuterium and a hydrogen, then hydrogen is lower. Your professor's trying to trick you. Tell them it's not nice and just stick to hydrogen. The second trick that I want you to recognize, and this one is going to save you a lot of time later, is look at what we had for number 3. We have a methyl group. Methyl groups come up a lot in stereochemistry. A methyl group is just a carbon and hydrogen. What is the second lowest atom on the table here? Carbon. And what is the lowest substituent I can have on a carbon? Hydrogen. So the absolute lowest, unless I have deuterium, which is a trick, the absolute lowest I can have after hydrogen is a methyl group, second lowest atom with the lowest atom on it. And so you don't have to bother ranking it. Just know that if you have a methyl in the presence of a hydrogen, then methyl is going to be an automatic 3 and hydrogen is going to be an automatic 4. If you have a methyl without hydrogen, then it is the lowest, and that's your automatic number 4. So in a molecule like this, we didn't even have to look at the table for everything. All you would have to do is say hydrogen, automatic number 4, methyl in the presence of hydrogen, automatic number 3, and then you're simply left to go between oxygen and bromine. And then it's just one comparison that you have to make on the table, and you're good to go. So this is hopefully going to save you time. If you're with me, if this is making sense, let me see thumbs up in the comments. Let's see. I did microbiome today, and apparently it's important to know the lore of why something is chiral or achiral. What do you mean the lore? I'm trying to think. In microbiology, where did that come in? I guess if you're talking about enzymes and the stereochemistry of it'll attach to something that has an R versus an S. But if something else, I'd be very curious. It's been ages since I was in microbiology. All right, so we have our basics. Let's crank it up one notch at a time with each example. The goal being to learn how to do the really complicated stuff, never getting lost in the process. So we'll start with our skeleton again, and this time I'm going to put the CH3 over here. I will put the hydrogen here, and we'll do iodine and an SH group. I don't expect you to have this memorized yet, so we'll put it on the side. Let's go through the steps. I'll show them to you again. Rank the substituents, put number 4 in the back, cross it out, arc 1 to 2 to 3. Is it R or S? So let's go through it. We're not going to start with the table. I have a hydrogen, automatic number 4. I have a methyl group in the presence of hydrogen, automatic number 3. All I'm left to compare is iodine and sulfur. Iodine is always your highest priority when you're dealing with just your standard atoms. And so iodine will be number 1, sulfur will be number 2, and step 1 is complete. Oh, you mean the DNL amino acids? Yeah, it actually started with glycerol, I want to say, or one of those little sugar molecules, and everything kind of evolved from there, which is pretty cool. It's pretty amazing how scientists were able to figure these things out with the primitive tools they had at the time. But I love the tools we have today because it makes it so much easier, and we can get so much more out of it. Now that I have my substituents, step 2 was to put number 4 in the back. But number 4 is in the front. So how do I put number 4 in the back? Let me know in the comments. I'm curious. What did your professor tell you to do for this step? I have heard of students building model kits, which if you build the model kit, you put your 1, 2, 3, 4s in the front, then you flip it around. I guess in this way to you, it's in the front. Then you flip it around and manipulate it and waste time and try to remember what color was what atom. That was option number 1. The other things I've learned is to kind of picture it in your head. So you build the model kit and then you kind of turn the molecule and do mental gymnastics. And no, so the mental gymnastics I think are even worse. Model kits are a waste of time. So here is what I want you to do. Let's go back to this. Let's turn this into a 3-dimensional molecule. And for my American students, we're going very patriotic here. If you're not American, we're just going to go with patriotic in the honor of I live in the US and I love my country. So red, white, and blue. What direction do you see it? Clockwise or counterclockwise? In the order I said. Red, white, and blue. Red, white, and blue. If you are seeing it as counterclockwise, which is what I'm facing at the camera, you're absolutely correct, except I don't see counterclockwise. I see clockwise. So how is it that I am holding one molecule in my hand? I'm showing you the same thing I'm looking at, but you're seeing counterclockwise and I'm seeing clockwise. How is that possible? Here is what I see. I'm looking at it this way. This is how I'm seeing it as I'm showing it to you. And now, if you look red, white, and blue, That's clockwise to you, isn't it? It doesn't have to do with the camera being flipped. Actually, that's a good point. I don't know which way you're seeing it, but look at it this way, right? Whatever you see right now, I am behind it. I'm behind it, so I see it backwards. This is what I see. So notice how when I turn the molecule around, the red, white, and blue switch direction. It's simply because am I looking at it from the front or the back to front? And that is key. If I'm looking at a molecule, I only care about the 3 forward substituents. So the thing that's in the back is out of the way. Now, when I'm teaching this to you, I'm showing it to you with red, white, and blue facing you. The thing that's in the back is out of the way to you, but not to me. In order to show it to you in the front, I have to hold the molecule backwards. And so if you were holding this molecule and showing it to a friend, you would do the same thing. And here's the thought process you're having in your head. Red, white, and blue. I, as I'm looking at it, see it going clockwise, but I know you're looking at it from the other side. So if I see it clockwise, I do a flip and I tell you out loud, counterclockwise. Red, white, and blue. Red, white, and blue. I see it counterclockwise, but I'm showing it to you backwards, so I will say the flip out loud. So I do it, and then I flip it. I do it, and then I flip it. That is the mentality that we want to use when we're looking at a molecule like this. So just imagine that you are looking at this molecule, red, white, and blue. 1, 2, and 3, but 3 is in the back, 4 is in the front. We are showing this to someone who is looking at it from the other side, because if somebody is standing there behind the molecule, number 4 is in the back to them, and that is how we want it. So in this situation, specifically, where number 4 is in the back, you're going to follow the same steps. We ranked 1, 2, 3, and 4. We cross out number 4. Then we trace an arc from 1 to 2 to 3. And remember, we're seeing it backwards, so we're going to reverse it. And that is how I know that this thing is R, and I don't need to build a model kit. I definitely don't need to do mental gymnastics. Another one you'll see is to be told to rewrite it. I learned to kind of move the molecule on the paper and flip it, and I don't do very well with like picturing. To this day, if I am in my basement, I cannot look up and tell you what room is there, because it's like the basement and the house are oriented differently. And so I have to think, okay, I'm in this room, but the steps go, I don't know what's above me. I'm just going to be, it's like, you have to be quiet because the baby's room is up. Yeah, whatever you say, I'm going to trust you, because the mental gymnastics don't work for me. So I need something on paper that I can fully trust. Can you do another example, please? Absolutely, yes. Let's do another one. Should we treat wedges as handles like the black ball you're holding? Yeah, okay, I like that. So let me demonstrate what Angel is saying, because that's really good. This is a handle. I am holding it. Oh, wrong one. This is a handle. I'm holding it and I'm showing it to you, but then I go 1, 2, 3, and I turn it backwards. So we have to have the handle out of the way so we can look at it. Angel, I love that. Excellent. Yeah, let's do that. So let's do another example just to make sure that this makes sense. Let's go with a carbon skeleton that is 3-dimensional. And let's take some random substituents. We'll put an alcohol, a methyl group, a bromine, and an amine. A nitro, and not nitro, just an NH2. All right, so we need the periodic table, which you will have memorized. I want to see fire in the comments that you're going to take the time to memorize it in the next few days. And let's begin ranking. We have bromine, oxygen, carbon, nitrogen. Bromine, oxygen, carbon, nitrogen. We don't even need to look at carbon on the periodic table, because the moment you saw a methyl group without a hydrogen present, that's your clue, automatic number 4. Then we have the rest. Bromine is highest priority. That is number 1. Oxygen is number 2. Nitrogen is number 3. Number 4 is coming forward. So we're going to follow the steps and then reverse it. So we have number 4, cross it out, trace an arc from 1 to 2 to 3, and then reverse it. This molecule is S. Oves, let me know if this is clear. Let me know if it makes sense, because this is the first level of trickiness that shows up, and I want to make sure that you're with me. Excellent. Let's look at another one. And that is, we'll take the carbon. Go ahead and type your favorite substituents or atoms that you want to see. And we'll come up with a fun molecule together. Actually, I forgot there's a very serious time delay here. So let's see if we can get these coming up. I see a chlorine. Let's put that over here. Let's get a hydrogen. Let's get a carboxy and an alcohol. All right, what are we comparing? Hydrogen is an automatic number 4. Then I'm left with chlorine, carbon, oxygen. Chlorine, carbon, oxygen. Chlorine is number 1. Oxygen is number 2. And carbon is number 3. Notice I only looked at the atom that is directly attached to my chiral center. I'm only looking at the carbon. Even though it has so many oxygens, it doesn't count. It's only ever that first atom. Chlorine will be kicking my tail with resonance. All right, well, let's take revenge on chlorine over here. Notice that, well, I have my substituents ranked, but here's the problem. Number 4 is in the plane of the page. It's a line. It's not a dash. It's not a wedge. It's not coming forward. It's not coming back. So I can't treat it like it belongs there, but I also can't treat it like it's in the back and flip it around. This is where it gets tricky, and this is where most students lose time or points on the exam. So we are going to take a pause on the paper and play with some model kits. Now you know why I don't have the green ones, because I use words like play with the model kits, and my 3-year-old thinks it's a play. So here we have our 2 molecules. Both are chiral, and I don't know what chirality I set up, so let's do this. All right. They are perfectly superimposable. Everything perfectly lines up. It is the same exact molecule. If I try to take this molecule and put a mirror between it, I can line up the blue and the white. The black is in the back, but look at the red. One is up, one is down. That's no good. If I bring the red up, the black and the red are good. The blue and white are no good. If I switch the blue and white to be perfect mirror images, the black and the red are no good. No matter what I do, because these 2 molecules are the same exact thing, I cannot turn them into mirror images. So now this is not a magic trick. I'm just putting this one down. I'm not doing anything scary. All I'm going to do is take 2 random substituents and switch them. So I took the thumb of this imaginary hand and I put it on the other side. So that is how you turn a right hand into a left hand. Now I take my molecule and I can make a perfect mirror between it. Notice that everything is perfectly mirrored. My hands are a little drunk here, but the molecules themselves, everything is perfectly lined up. White, black, blue, red is in the back on the outsides. No matter how I twist it and fumble it and everything, let's see if I could build this mirror again. I have white on top, red facing you, black in the back, and blue right there. I turn it, same thing. The black and the white are facing. The red are towards you in the front. The blue are mirrored in the back. Everything is the same on the mirror. And then if I try to superimpose them, the blue and white are good. The red and black are not. So I'll switch it and I'll make the red and black the same. but now the blue and white are not the same. So all I did was make one swap. It doesn't matter what I swap. I just took any two substituents, randomly took them off, switched them, and a molecule that was the same thing became an enantiomer. If I do this again, I don't remember what I switched before, so I'm switching two more groups at random, and I got the blue and the white this time. Now, what was a perfect mirror image is no longer a perfect mirror image. The blue and white are the same, the red and black are not. If I make the red and black the same, right there, red and black, the blue and white are not. If I line them up, though, one on top of the other, it's perfectly the same thing. So what I did, and this is key, I took a molecule, I made one swap, I turned it into the opposite. I did another swap, I turned it into the same thing. So let's see what we can do with that on paper, because that is key to understanding what is going on here. If I take a molecule and I do one swap, I will turn that molecule into an enantiomer of what it was. If I take that molecule and I do two swaps, meaning I swap and then another swap, no matter what that second one is, I wind up with the same thing that I started with. I showed this to you on the model kit. Now I'm showing it to you here. If I then do a third swap, what do you think is going to happen? I'm going to wind up once again with with the enantiomer of what I started with. If I do 4 swaps, I will wind up with the same thing as what I started with. If I do 3,471 swaps, what do you think is going to happen? Well, these are all odd number of swaps. I should wind up with an enantiomer. If I do 26,472 swaps, I should wind up with something that is exactly the same. If this makes sense, let me see yeses in the comments, because this is the biggest trick I can teach you today to save you so much time. Let me prove it to you. The key is, it doesn't matter what I swap. You notice I just randomly grabbed 2 substituents and pulled them off. It doesn't matter what they are, so long as I count how many swaps I do. So here we go. Rule number 1 was rank the substituents. Rule number 2 was put number 4 in the back. So let's keep track. Let's keep our accounting very clear. The first swap that we're going to do is put number 4 in the back. So here I'll put number 4, and that means 1 has to go here. This gave me the enantiomer of what I started with. Now, I don't want any confusion, so I will always do a second swap, because the second swap is going to undo the first swap, even though it's any other groups, because then if I have an even number of swaps, the molecule will have the same exact chirality as what I started with, and then I can very easily rank them. Welcome, Jojo. It is good to see you. Put live notes in the comments for a link to download the notes from tonight. That way you can just jump in, catch up, and not worry about what you missed. You'll have all of that later. For my second swap, it doesn't matter what I move, so long as I don't touch number 4, because I need to have that in the back. And so let's do that. 2 and 3 as my random second swap. I have a total of 2 swaps. It's an even number of swaps. That means the chirality of the new molecule is the same as... Oh, I got ahead of myself. Ignore everything I just did here, because I want to show you something else. And then I'm going to come back to that. Okay, swap number 1 is putting number 4 in the back. So just a reminder, we had 4, 1, 2, and 3. To put number 4 in the back, I swapped the hydrogen and the chlorine. I completely forgot what I was swapping there. And then here I'm going to swap, let's do a different color. I'll swap the alcohol and the carboxy. So I'll put the OH here and the carboxy over here. And now I can re-rank them. So let's get rid of the numbers. Let's rank them again. Oh, no, wait, that was, yeah, that's my two swaps. That means the chirality is exactly the same. And this time when I rank it, I have 4, 1, 2, 3. Number 4 needs to be in the back, which conveniently it is because I put number 4 there. Trace an arc from 1 to 2 to 3. The top of the arc goes to the right. It is R. This is what I meant to show you. And then I was going to ask you if this made sense, but also if it feels like it's taking so much time because you have to redraw all those substituents only to then re-rank it and get the numbers in the right place. So option 1 is well, actually, let me show you the real options. Option 1 was to do this with a model kit. This is what a lot of professors teach. I'm going to say absolutely not. It's a waste of time. Option 2 is faster than a model kit, and that is doing mental gymnastics. But for the average student like myself, mental gymnastics are too difficult. This is where option 3 comes in, and that is the swap method. You can swap the groups, which is what we just did here, but even that is too time consuming, so we'll go with option 4, and that is only to swap the numbers. So that is where I accidentally jumped ahead and started swapping the numbers. The idea here is that if I put a hydrogen here and then ranked it, I would get a number 4 here anyway. So why would I waste my time with the atoms if I could just put the number 4 there and just move the numbers around? And the same thing still works. Cross out number 4, trace an arc from 1 to 2 to 3. I got R. What did I get when I drew it? I got R. But this one took so much longer because I had to redraw all the groups. And I don't want to do that. Let me see a mind-blown emoji in the comments. If this is going to save you time, confusion, and give you so much confidence on the exam because of how straightforward and fast this is. That's the key. It's fast, and you know you did it right, which is going to be so much easier. While you're typing that in, I'm going to start with another one. We'll take a molecule that has, why do I keep doing this in blue? I don't know. So we'll take 4 substituents, and this time I'm going to make it a little bit more fun. We'll have a methyl group, a carboxylic acid, a carboxy, an ethyl group, and an isopropyl group. We're looking at the periodic table. You know what? I need to make some changes here. So I have ADHD. And if I were to, oh, I didn't realize I had that on my clipboard. That's not what I was trying to copy here. I have ADHD, and if I were to teach this the way most people do, I would lose my mind. So we are not going to do that. I have too much to focus on. We are going to follow the colors. That's why I do everything in colors. So we'll have purple, we'll have green, we'll have blue, and we'll have pink. Why not? The atoms that I lost from my clipboard, I'll just redraw them. H, C, N, O, F, halogen, Cl, Br, I, sulfur, phosphorus. Back on my clipboard, and let's see what we're going to do with it. I need to choose priorities for carbon, 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 carbon. That's going to be a problem. ADHD friendly method is pretty much all I teach, because if I, as the teacher, am getting lost, you as the student are probably also getting lost. Like, you can tell when your teacher doesn't know what's going on. My biochem professor was so advanced in his hemoglobin research, because that's what his specialty was. He forgot the basics of RNA, so he kept asking me to check his work in middle of class. It was awesome. So we have, well, a lot of things to rank, and they're all carbon. So how do we rank something if the atoms are all the same? This is where we do a next step. So if the atom you're looking at is the same, and that's the atom directly connected to the chiral center, what you're going to do is rank the next atom, but you're only ever going to that one next atom. So the reason I did it in color is I want to be able to very clearly draw each of them out. We have the carboxylic acid. We have the isopropyl group, which is like this. We have our ethyl group. I'm just drawing the pieces that we need to see. And then what am I missing? The methyl group. Now the methyl group, you wouldn't ever have to do this because you know the rule. Methyl in the absence of hydrogen is automatically number 4. But I'm showing you here just so you can really see it all together. The first thing we did was look at the atom directly attached, that's not an atom, to the chiral center, and it was a carbon. If they're all the same, what you're going to do is cross it out and look at the highest priority atom on the atom you just crossed out. And so now I'm going to look at, this is oxygen, oxygen, they're all attached to the green carbon, so I could pick any oxygen. This one has 2 carbons, I can pick one. This one has 1 carbon, this one has a hydrogen. We're only looking at the highest priority. So now we're comparing oxygen, carbon, carbon, hydrogen. Hydrogen is automatically number 4, making methyl 4. Oxygen is the highest in the secondary priorities. That makes this number 1. And here I'm comparing carbon to carbon, so they cancel out. This is where students get confused. I don't look at the next atom on the chain. I go back to the first carbon I crossed out and I ask, the first one you brought to the table didn't work. Give me your second one. What is the second one they can bring to the table? Well, this carbon here, the second highest priority is another carbon. This carbon here, the second highest priority, still directly attached as a hydrogen, and that is my point of differentiation. We already have a priority 1, making the carbon priority 2 for the isopropyl group, the ethyl priority 3, and then we already have number 4. So do you see how I did it? I went to the next atom, and on that next atom, I compare them one at a time until I find that point of difference. Then I can rank them. So we have our substituents. Number 4 is coming forward, which is the easier one because all we do is cross out number 4, arc from 1 to 2 to 3, and then reverse it. This molecule is S. I want to show you another one like this, even faster. First, let me know yes or no in the comments if what I did here made sense, because you need to understand the long way before I can show you the shortcut. Otherwise, the shortcuts are just going to be confusing. So yes or no in the comments if you were with me there. We'll have our central carbon atom with 4 substituents. We'll make it a little bit trickier this time. So I'll give you a CH2, CH2, CH3. Here we'll have a CH2, CH3. Here we will have a C, CH3, and then we'll make this a longer chain like that. And then here we'll have a CH2, CH2. I'm going to show you a trick with this. So we'll go with CH, CH3, and CH3. Okay. I think, actually, you tell me, easy, medium, or hard, given just what is going on. And we are missing a hydrogen right there. Let's make that look like it belongs. We'll just make it CH. Like, it does not want to look like it belongs. CH. There we go. Now it belongs. Angel, challenge for you. Mostly with me means there's a little bit of confusion. Confusion builds, builds, builds. You're overwhelmed. What are you confused about? What is that one piece that's missing so that everything will click? That's what I'm looking for. Can you repeat what you did in the bottom, like how you rank them? Yes. What we do is if I have an atom A and another atom A, and then we have B and C and D. We look at A, If it's the same, we cancel it out. We look at B. If it's the same, we cancel it out. But then we go back and see what else is on A. So we always look at the atom attached to the chiral center, what else is on it? And then once we exhausted everything directly attached, then what else? Then what else? Ranking the carbons against carbons. So Angel, yes, I figured that we would need a second one, and that's why I have this. So let's start from the beginning with this one. This is my chiral carbon. It has 4 unique substituents. I have an ethyl, a propyl. This looks like a butyl, and this looks like a pentyl, but they're isomers, so they have branches there on purpose. So it's a sec-butyl, and then the next one is 5 carbons. To rank substituents, we have to start with the atom directly attached to the chiral carbon. And so that means I'm comparing carbon to carbon to carbon to carbon. Well, carbon to carbon is the same exact atom. That means I cannot compare them. That means I have to do something else. I have to cancel it out and say, if you are all exactly the same, what is the first point of difference? So I look at the highest priority on that carbon, meaning what is the next, that first step that's different. So at the dark blue substituent, directly attached to carbon, I have a carbon. Directly attached to carbon, I have a carbon. Directly attached to carbon, carbon, they all have directly attached carbons. So here's where we can take a little bit of a shortcut and say, how many carbons are directly attached? 1 carbon, 1 carbon, 2 carbons, and 1 carbon. If I have 2 carbons on that carbon atom, that's because the green one, if you look at it, it's carbon, hydrogen, carbon, carbon. That's not right there. Whereas this one is carbon, it's got the carbon and 2 hydrogens, carbon and 2 hydrogens, carbon and 2 hydrogens. So if you see a branch, that is your clue that you have 2 carbons, which is higher priority than carbon and hydrogen. So the first branch that I hit in this case is my highest priority. For all of the other ones, the reason I looked at simply the group attached is because if I can say this is a CH2C, this is a CH2C, a CH2C, it's just a faster way to say CH2C. They all have a C, all have an H, all have an H. So I can go to the next branch. If the chain ends, it's lower priority than a chain that continues. So let me start it as a rule and then show you why so that you can remember the rule and get it right. If the chain ends, it's going to be lower than a longer chain. Why does a chain ending make it lower priority than a longer chain? Let's look at just those 2. I have the ethyl group. And then I had the propyl group. So let's draw that out. I have a CHH, CHH, and CHHH. As I'm working through this, if you have not subscribed to my channel, make sure you do so right away. Pretty please. I am hoping to at some point hit 1 million subscribers. 1 video, 1 live stream, 1 short at a time, but I'm going to need your help. So pretty please, I would be really, really grateful if you can do that. And then let's look at this. Let's compare them one at a time. Carbon to carbon is the same thing. Highest priority on the carbon I crossed out is another carbon, a hydrogen and a hydrogen. Notice that I went to all 3 bonds around this carbon first. If the entire first part of this was crossed out, I then go to the next highest priority. And notice that when I have a chain ending versus a chain continuing, the chain ending means that I have hydrogens that are the same, but now it's a hydrogen to a carbon. Carbon outranks hydrogen. This is why a longer chain, if everything else is equal, the longer chain beats the shorter chain because the longer chain has a carbon where the shorter chain has a hydrogen because it's ending. Let me know if this concept is clear because this is one long process simplified. That's one less thing you have to worry about when you're looking over here. 2 carbon chain, 3 carbon chain. That tells me that this is lower in priority than this one. And then we had already talked about a branch being higher priority than not a branch, and I think I showed that to you as well. So the way we can look at this faster, instead of doing it the long, long way, because we already figured that out, but I'm going to show you this the way I do it with the shortcuts. Each one starts out as a carbon. The first one has a branch. That means it's got 2 carbons on it, and this assumes there's no oxygen. This is strictly a carbon-to-carbon comparison. 2 carbons on it because the branch is hit right away. That's priority number 1. Then here we have a CH2, CH2, CH2. All of them are the same. Here I have a CH3, CH2, the chain continues, CH2, the chain continues, lowest priority. Here the chain ends at the 3rd carbon. Here I have the chain branching after the 3rd carbon, number 2, number 3. This is much, much faster. I realize I went kind of fast here. So make sure you practice this a few times, watch the recording, go through it, make sure you understand it, because then you can say priorities are ranked really, really quick. Number 4 is not in the back or in the front, so we'll keep track of our swaps right over here. And then what we'll do is put number 4 in the back. So I'm only going to move the numbers. 4, 3, that's an odd number. Let's do another set. It doesn't have to be this other 2. I could swap anything. So I'm randomly going to swap 3 and 1. I'll put 1 here and 3 here. As long as I don't touch number 4, I'm good. That was a second swap. That means I have an even number of swaps. My stereochemistry is exactly as I started. Now I can cross out number 4 in the back. Trace an arc from 1 to 2 to 3. Top of the arc is not to the right. It is not R, it is S. Very, very good question. The purple chain is longer than the green question. So why is the purple chain lower in priority? I'm so glad you asked. So let's take a look at green branched, 4 carbons, purple branched at the end. Let me draw them out in detail. So green immediately hit a branch. So I had a carbon with a CH3, and then it had a hydrogen, a CH2, and a CH2. The purple one had a CH2, another CH2, another. This one had a CH3 on it, a CH3 on it. Okay. So this is technically a longer chain, right? The length of the chain is only valid if there are no branches, because when I start out, I have a carbon. They're exactly the same. I rule them out. The next thing on that carbon is a carbon and a carbon. Let's do the same spot so you can see clearly what I'm doing. A carbon and a carbon, exactly the same. I have to go back to that first carbon that I crossed out in red and ask, what is the next highest priority on it? The one with a branch has a carbon. The one without a branch has a hydrogen. Carbon beats hydrogen. So a branch has an extra carbon early on. The branch will always beat the linear because it has that extra carbon early on. And that is why the shorter branch chain still beats the longer chain, even if this thing went on to infinity, because we never had a chance to look that far. We immediately saw a reason to differentiate them. Jojo, that is a really, really good question. Let me know if that makes sense, because that is critical. Going back to here, we had our priorities ranked. You know what, Jojo? That inspired me to do another question. We are totally going past an hour today. I hope you guys are okay with that, because I just like to talk too much about these examples. Let's do an alcohol. So we'll do a CH2OH. we'll have a CH2, 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 CH3. Here we'll have an isopropyl, which is a CH3 and a CH3. And then here we'll have using the dark. Okay, so we'll do a CH2, 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 CH2. We'll go all the way down here because I'm running out of room and put a COH and put another COH. This is totally not a stable molecule with a diol, but for the sake of this argument, it's 2 alcohols. All right. So you're looking at this and thinking, you know what, let's put branches on here. Let's go nuts with this. I want to prove a point. So if I can make it really exaggerated, I think my point will be proven. So we'll put a CH2, a CH2, a CH. I'm trying to go in that direction. Like that. And a CH2. And now we'll put a carboxylic acid at the end. Okay. So we have, oh, I missed what I was trying to do. I was trying to do a branch. Okay. So this thing right here is a very long chain, and it has a carboxylic acid, and it's got branching. It's got so much going on. But here's the thing. We start at the first carbon atom. Cross it out. It's exactly the same. Highest priority on the first carbon atom. Oxygen, straight chain, branch chain, straight chain. Oxygen wins because it beats carbon. Branch chain wins because it beats the linear. And then this one is a total of 4 linear, 1, 2, 3, 4, 5, 6. It takes 7 until the branch. So even though this thing has a really long chain and a branch and a carboxy group, it's priority number 4. No, I'm sorry. It's priority number 3 because I needed to put a branch into that one. Yeah, no, this is priority number 3 and this is priority number 4. Why is this priority number 4? Because this goes 4 long. This goes more than 4 long, longer chain, beats shorter chain as long as everything on them is equal. And so, hey, 4 happened to be in the back. That worked out conveniently. Cross out number 4. Trace an arc from 1 to 2 to 3. This thing is R, and I didn't have to draw anything crazy. We basically cycle through all the bonds. Yes, 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 yes. If the highest priority is not enough, then we go to the next highest, the next highest. We run out of everything. We cycle through all the attachments. Then we go to the next one. Then we go to the next one. Then we go to the next one, and so on. All right. In the interest of time, I'm not going to go into too many shortcuts, but I do want to show you this really, really important one because this is the other one guaranteed to save you time on your exam. So we'll start with a carbon skeleton. One way professors like to test this topic is to ask you the relationship between atoms, between molecules that have the same substituents. So we'll put an alcohol, a methyl group. We'll put, I'm just going to put another alcohol. Let's put an ether on it. And we'll put a bromine. The way that you are taught to solve something like this is option 1, build a model kit and then start doing all those rotations, which you're not going to do. Option 2 is, and this is the straightforward, this is the way to teach it. Find out if this molecule is R and S. Find out if this molecule is R or S. And then if they're both R, they're the same thing. If they're both S, they're the same thing. If one is R and one is S, then they're enantiomers, right? Does that sound like the perfectly plausible, straightforward, figure out what the relationship is? Thank you so much, Kevin. I appreciate it. First, going back, high atomic mass, branching, chain length. Yes. Branching with the same substituents. And that is the shortcut. You could always default to the proper way where you literally go atom, 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 cross, cross, atom, cross, atom, cross. The RNS method is the way to do it. But Here is the method that I prefer. We'll call this molecule A. We'll call this molecule B. We're going to keep track of swaps, and we're going to say as follows. How many swaps is it going to take to make molecule B look like molecule A? Molecule A has a methyl group at the top. So let's do our first swap to put a methyl group at the top. Now, molecule A has an OH on the right. Oh, we have to count the first swap. Molecule A has an OH on the right, so let's put the OH on the right and the OCH3 here. That's 2. Molecule A has a bromine on the left. Why did I just put the bromine back where it belongs? Where it was? Bromine on the left and then OCH3 to the right. It's an odd number of swaps. Notice everything is perfectly lined up. If it took an odd number of swaps to get molecule A and B to look the same, I know that odd means they are enantiomers. And I never wasted time finding if the molecule was R or S because I didn't need to. It was so much faster to do it that way. Just to prove it to you, because I only ever want you to trust the trick if you know how I did it. If you can't peek behind the curtains and understand the trick, that trick is useless. So let's solve this the long way, just to make sure that we're confident that the trick works. We have oxygen, bromine, oxygen, methyl. Methyl in the presence of hydrogen is 3. Absence of hydrogen is 4. We'll put a 4 for both methyl groups. Oh, I no longer have the table. Let's do it again. HCNO. FCl, sulfur, phosphorus. Okay, so that way you can see bromine is the highest priority at number 1. Oxygen to oxygen. Oxygen with a hydrogen is lower than oxygen with a carbon. That is 2. That is 3, 2, and 3. For the first molecule, I have number 4 in the plane of the page. So if I keep track of my swaps, I move number 4 to the back. That's 4. That's 3. I'm going to do a second swap, 2, 1, even. And then I find out that, and I'm doing this really fast to prove a trick. This is R. Let's do the same thing for the other one. 4, once again, is conveniently not in the back. So we'll keep track of our swaps over here. We'll put 4 in the back. That's not 4. 4 and 2. 4 and 2. 1 and 3, 2 swaps, even. Now I can cross out number 4, trace an arc from 1 to 2 to 3. This is S. R and S are enantiomers. What did we say this was? Enantiomers. But wasn't it so much faster to just compare them without finding R and S? Again, I went through this really fast because I was proving a point. If you're going to try RNS, please, please, please do it slower until you feel really confident. But this right here, much, much faster. OMG, this feels illegal with how simple it is. Jojo, if you can save time on the easier or the more doable things, if this can be the easy points on your exam, then now you have more mental capacity to work out the harder questions. And I mean, that's going to ultimately wind up on a higher score. Why is my screen acting like it wants to die? All right, I kind of want to wrap up here, but I did open with this one. Let me know in the comments if you have learned Newman projections, because this is the type of question that professors like to torture you with. This is more advanced. If you didn't learn this yet, just bookmark this, come back to the video after you've learned Newman projections. There you go. Angel, yeah, just take it with a grain of salt and focus only on what you need. Ovase, same for you. The thing about Newman projections is that they are showing you a very different way to look at the molecule. And typically, the way teachers will tell you to solve this is one build a model kit. I'm going to say absolutely not. 2, they're going to tell you to convert it back to a bond line drawing, to redraw the molecule. That's too much work. So here's what you want to do. First, make sure that the substituents in the front are the same, whether they're clockwise or counterclockwise, and the back, to make sure that you have the molecule lined up the same way. The front is green. If you haven't learned this yet, just take this with a grain of salt. The front is green, and notice that I have the same 3, bromine, methyl, oxygen. So what I'm going to do is simply look at the direction that they go and determine if they're the same or opposite. It doesn't matter which 3 I take or which direction I go. I simply want to go direction. My model kit, I could have picked any 3 colors, any direction. I just need a point of comparison. So I am going to use the point of comparison from methyl to oxygen to bromine. Methyl, oxygen, bromine, this direction. Methyl, oxygen, bromine, that direction. The forward carbon is opposite. So the green, the forward carbon is a mirror image. Let's hold that thought. Let's do the same thing for the rear carbon. Well, the rear carbon is actually achiral because it has 2 hydrogens. So this is not going to have a potential diastereomer. If the forward carbon, which we have confirmed is chiral, is going in opposite directions, these 2 molecules are enantiomers of each other. And I can tell you that with certainty, having A, not bothered to find if it's RNS, and B, not even bothered to make one look like the other. All I did was look at the Newman and ask, do you spin the same way or this? I can't do that. Are they spinning the same way or are they spinning opposite ways? Because these are spinning opposite ways, these 2 molecules are enantiomers of each other, and I'm good to go. Brian, thank you so much. Brian, I really, really appreciate it. I hope that you found this session really, really helpful. And mind blown in the comments if this is going to save you time. And the same thing works for Fisher projections, but with the Fisher, you want to do it this way. The Newman is where most students just get so overwhelmed. You do this, you're good to go. Now, I realize we went through a lot today. It's a lot to process. So I want you to just take a step back, let it sink in, come back to the session. Don't worry about the notes again. Just put live notes in the comments. I've got you covered. I will send you the PDF of everything that I drew today, including, I completely forgot to tell you something, including, I don't know where I was going that. Oh, even if you're watching the recording, then I will also send you that. What I was going to say is we started with beginner practice today, but if you want to really get good at this, you have to drill, drill, drill. And that means you want to do more practice, which I actually have something for you. I have a stereochemistry worksheet that is not available on my website. The stereochemistry worksheet just goes through a bunch of different practice problems. Angel, thank you so much. I really appreciate that. The stereochemistry worksheet goes through just a bunch of different problems from the basics all the way to more advanced. Not available on my website. Just put worksheet in the comments and I will send you the link. Yes, even if you're watching the recording. And study hall members, Angel, you have access to the solutions. And if you get stuck on something, you could just grab a screenshot and post it to the group and say, hey, Leah, how do I work through that? Or just whatever you're stuck on, and I will help you. So again, live notes, and let me just grab live notes in the comments for this session. Notes, worksheet for the work. I meant to tell you about the worksheet like half an hour ago. So for those of you who joined late, we have had one of those weeks where it's like, just take a deep breath. This too shall pass. Our AC went out. The next day, our oven broke. The glass just exploded. And then I went and tripped, which I think it's related because I was so distracted that at least I got my run in first because I'm training for a marathon, which is why we had our mirror image Band-Aids today. All right, let's see. Thank you so much. And you are very welcome. Thank you. So this is just one topic in organic chemistry. And if you found today helpful, if you found today helpful, if you liked the way I broke things down, and you like to see every topic in organic chemistry 1, Orga 1 and 2 broken down like this, with me actually focused, because I feel like today I was not as focused, then I would love for you to come join me in the Organic Chemistry Study Hall. That is my membership where I have videos covering all of Organic Chemistry 1 and Organic Chemistry 2, as well as, and this is something exciting, Angel, I think I may have hinted it to you already, I am I'm moving the study hall onto a new platform that is so amazing because you'll have the videos, the worksheets, the community, the place to ask questions, all in one place. Right now it's using a Facebook group, but the new platform is all off social media, so you can have all your questions in one place. And Angel, I think I told you this as well, I am thinking of bringing back bonus live sessions for members only. So the worksheets, that is something new that I recently started adding, like the worksheet that I mentioned today. It's not available on my website, but what I'm going to do is, I'm going to confirm this at the end of the month, but I'm thinking of doing one live session a month where I'll pick a worksheet topic that covers just one of the new worksheets that many students are working on at the time, and we will solve it together. So it's kind of a session like this, but instead of a teaching session, it's a let me teach you this problem and this problem and this problem. So it's just a ton of practice that you can work through and learn the what, the why, the how. Thank you, Angel. So that you start with the study hall video to learn, but then you get the detailed practice work through to make sure you really learn it from the study hall. Donald, thank you so much. What? Hold on, something just popped up and I was confused. No, I don't want to do that. So if anyone is interested in the study hall, you can to liveforsci.com/join. That is the link to sign up. Or if you have any questions, just email me and I'll be happy to answer. All right, since we are definitely way past the hour that I was planning to go here, I'll go ahead and wrap up here. As I'm working on saving the notes and getting it all wrapped up for you in email, I'm going to stay logged in because YouTube keeps me connected for a couple of minutes after I log off. So any questions you have, go ahead and type it in. If you don't get to ask your question in time, I do look back at the questions here, but you can also email me. Just respond to the email with the notes, or any email I sent you, it all comes from the same email address, and I will be happy to help you with anything you need. So on that note, have a wonderful evening. Thank you for spending your night with me, and I will see you soon.